Hey there everyone. So this is the next lecture that I wanted to do in the electrochemistry series. And this one is going to be going over thermodynamics and equilibrium and how we can tie that into electrochemistry. So specifically we're going to take a look at free energy, which is delta G, and we'll take a look at equilibrium, which is the K constant that we're used to working with, whether we're dealing with regular equilibrium, acid-base equilibrium, etc. K is just a placeholder for the equilibrium constant. It's a value that we put in there. So let's talk about that. What we really want to do is, now that we are familiar with creating a battery cell and we know the term E cell, we want to relate E cell over to delta G and K. And we're going to be able to do that through several equations. We can tie them all in together. And it turns out that if you know the E cell or the delta G or the K for any reaction, then you'll be able to find the other two. You need one of those pieces in order to solve the others. And there's some other basic information, constants and moles of electrons, that have to be plugged in. But of these three, if you can get one, then you should be able to tackle the others. So something that we want to discuss in regards to the electric energy for a cell or E cell is, when we're talking about E cell, it's really the volts, okay, times the coulombs. And coulombs is a term in chemistry that we use when we are referring to electric charge, specifically for electrons. Okay, so if you're thinking about it, when we talk about this, we can also set this equal to joules, right? Because joules is our unit of energy. Now, sometimes we're using it from a thermodynamics perspective when we're talking about heat. You can also talk about it from an energy, like an electric energy perspective. Now, we have to tie coulombs into that. So this all sort of interrelates. But joules is our general energy unit. Joules or kilojoules. So one of the very important pieces of information that we're going to need to tie all of these in together is relating moles of electrons to charge of electrons, which is a coulomb, and then mole would be Avogadro's number. So if you take the coulomb value times Avogadro's number, that will tell you the charge that is carried per mole of electrons that are going to be passing through. Because, right, we're sending electrons through a device or powering a voltage meter or whatever it is, and they're cycling over and over again. So it's not just one electron in theory, it's a whole bunch of them. So when we do that, we want a unit that can capture that information, and it turns out there is one. It's known as Faraday's constant, which we abbreviate with an F. And Faraday's constant is 9.6. It's around 9.65. It's really 9.647 if you're getting specific, but you'll sometimes see 9.65 written. Times 10 to the fourth coulombs per mole of electrons. All right? Very important number when we're dealing with electrochemistry. This is Faraday's constant. Now, what can we utilize Faraday's constant for? We can tie thermodynamic parameters, specifically the free energy of a battery, over to negative N, capital F, E cell. All right, so here we go. We've now connected E cell to delta G. Now you'll notice I have the standards here. So this is assuming we're operating at 25 degrees Celsius. And the bulk of the problems that we would practice or you would come across should be of that nature. Not always. We're going to have examples where they're not, but in general. So we've got delta G standardized and delta E standard, or not delta E, E cell standardized. Okay, so what is N? In this case, I mentioned it once or twice a minute ago. N is going to be the moles, and we're talking about stoichiometric usually here. It's the moles of electrons that are going to be transferred during this redox reaction. So if you remember, we were talking about balancing oxidation reactions, redox reactions. You find the total number of electrons that are going to be transferred in this process. So that value is very important. That's why we wanted to lead with that, because you're going to need to know what the value of N is, and the only way you can do that is by assessing these types of reactions and understanding the amount of electrons that are being passed back and forth. It might be simplistic for when you're just dealing with two metals, but when you have metal complexes, like when we were looking at some of the oxides and we had to balance with water, that can be a little more difficult, and you're going to have to figure out how many electrons are being passed back and forth in a case like that. All right, so obviously, like we just said, F is going to be the Faraday constant, and that will tie everything together here. Okay, so if I know the redox reaction, if I know what components are being utilized, I can determine E cell from my charts, if it's standardized. I know what the Faraday constant is, because that's not going to change. And then I can determine the moles of electrons from my half reactions, and I can utilize that value as N in order to find delta G. Now keep in mind here, because there's a negative, okay, N should always be a positive number. It's a stoichiometric coefficient. F will always be a positive number. Faraday's constant is a positive number. It's 9.647 times 10 to the fourth. So that means you have to look here. If E cell is positive, then delta G is negative, right? Because of that negative value. But if E cell is negative, then delta G is positive. And we know that a delta G that is negative usually corresponds to spontaneity, so a reaction that's going to go on its own. And so it is important that you realize a positive E cell is going to correlate to a spontaneous E cell, or a spontaneous battery that's generating this electric reaction, right? So keep that in mind when you're looking at this. This is sort of an important setup where the negative value is there. Okay, so one of the other things, because we want to be able to tie this into equilibrium, is that we can say that E cell is going to be equal to, now I'm not going to show you how all of this is derived. It comes from the R constant as well as temperature, and because temperature is 25 degrees Celsius, when it's standardized, we're putting that all in to get a value, okay? And the value is E cell equals 0.0257 volts over N, same N as before, and that is times the natural logarithm of the equilibrium constant. All right, so this setup right here can tie equilibrium constant in with E cell. So we now have two very useful reactions, okay, that all involve E cell, and then we can tie this together even further because we can relate delta G over to the equilibrium constant. So we can also say that delta G standardized is equal to negative RT, okay, ln K. So if I can find the K through either E cell or delta G, right, then I can connect these together. Now I do want to make a note here. The R that we're referring to in this case is a bit different than the 0.0821, which is the one used for gas laws. It is still the same R, but it's using different units, which means that it's going to have a different value. So the R that we plug in here is 8.314, and that's because it's not ATM liter per mole Kelvin, it is joules per Kelvin mole. Okay, and joules is important here because we're dealing with energy in these parameters. So we want to make sure that we're using the correct R value when we're dealing with this. All right, so what I'd like to do now, because we've got these three equations that we can tie together, is let's go down and do some practice problems. All right, so here's the first one. Calculate the equilibrium constant, so that's K, all right, for the following reaction at 25 degrees Celsius, and we have a reaction here. So we've got tin is going to tin 2+, and then copper is going from copper 2+ to copper plus. Now we have to be careful, it's not going to copper solid, so we have to pick out the correct value when we go in and we start pulling off standardized reduction potentials from our chart. Okay, so what I really should try to do here, if I want to find the equilibrium constant, which is K, I'm going to try to find what my E cell is based on this, because I can certainly go in and find the values at 25 degrees Celsius for E cell, right? And I should put a standardized note up here. So the question is, what would E cell, I'm sorry, not E cell, what would the E, standardized E of the tin 2 plus tin relationship be? Okay, so we're going to find that value. And we want to find the standardized E for the copper 2 plus copper plus value. Right? So what is that E? So what we'll do now is we're going to go ahead and pull up a chart with the standard reduction potentials. Okay, so here is the chart for the standard reduction potentials. And when I go through, I want to make sure that I am looking for the correct values. So let's try to find the copper 2 plus to copper plus. All right, so scrolling down. Here we go. Copper 2 plus to copper plus is going to be plus 0.15. Again, I take mine out to 2 decimal places. So it'll be plus 0.15 for the copper portion. And then I need to go find the tin. So tin is going to be SN. Alrighty, and here is tin. Okay, so it's tin 2 plus to regular tin solid. And that is negative 0.14 if I'm rounding, because it's negative 0.1375 here. So negative 0.14. All right. So those are the values that I'm going to utilize there. Let's go ahead and plug them in and find out what E cell is. Okay, so just to remind ourselves, this is 0.15, and this one we said was negative 0.14. Right, so in this case, we have to take a look which one is being oxidized and which one is being reduced as far as the cathode-anode relationship. So if we take a look, the copper is going from 2 plus to plus, so it's gaining electrons. It's being reduced, so it will be the cathode. So that means the copper needs to come first in the E cell equation. Right? Now remember, if you're just trying to set up your own battery and you're handed 2 of them, you would have to determine which one should be the cathode based on the values, which one's optimal in the way you want to set it up. Right? However, in this case, you're already being given a reaction, so you need to pay attention to which is the cathode and which is the anode. All right, E cell, the value that should go here would be 0.15 volts, okay, minus a minus 0.14 volts. Okay, so that means that E cell is going to be equal to 0.29 volts, and that's positive. So what I want to find is K, and in order to do that, I would rearrange the equation that I have up here. So if you see, I've got E cell, right, and then I've got this value here. In order to get ln K by itself, I'm going to need to multiply both sides by n. So that'll make it E cell times n. And then I would need to divide through by the 0.0257. So what I'm going to rearrange it to in a second is n E cell divided by 0.0257 volts, and that will set that equal to ln of K, and then we'll solve for K, because that's what the problem is asking. All right, so coming down here, what I'll do is I'll say I'm isolating ln K, and I'm going to set that equal to n times E cell. So n, in this case, how many electrons are being transferred? Well, if I take a look at this, I've got tin going to tin 2 plus, so it had to lose 2 electrons in that case. Now, is the copper gaining 2 electrons? Well, it goes from copper 2 plus to copper 1 plus, so that's a gain of 1 electron, but there's a stoichiometric coefficient of 2 in front of it, so it does it twice, so it's 2 electrons. Right? I don't really need to go and balance the whole half reaction set here to figure that one out. So I can put 2 as my n value. So what I'll end up with is 2 times the E cell over 0.0257 volts. And that is going to equal 22.6. So keep in mind, this is not the answer. This is the natural log of the answer we're looking for. Okay, now when you want to get rid of the natural log, not the base 10 log, you need to raise e, the natural logarithm antilog, so e to the 22.6. So k, okay, if you look on your scientific calculator, there's a little e. Okay, this is different than the e button used to put your exponent in for 10 to whatever. Okay, so it's little e 22.6 is going to be equal to, and if you solve for that, it's it is 7 times 10 to the 9th. Okay, so that is the k value that we have there. All right, now here's the next one. Calculate the standardized free energy, so now we're talking about delta G, okay, for the following reaction at 25 degrees Celsius. So again, if I'm at 25 degrees Celsius, why don't I go ahead and find the standardized E cell value? And if I can find that, then I could potentially move forward here. So I take a look. I've got solid gold going to aqueous gold 3+, and I also have solid calcium and calcium 2+. All right, so those are the values I need to go in and get. So I'm looking for the E of gold 2+, and I'm sorry, gold 3+, not 2+, and gold, right? And I also need the E value for calcium 2+ and calcium solid. So let's go find those values. Bringing our chart back up. Gold is AU, so we'll go to the top of this chart here and find AU. All right, gold 3+ is 1.498, so it's going to be approximately 1.50, so that's the value I'll put there. Okay, let's go ahead and mark that down. 1.50, and that was positive. All right, so then calcium, I need the calcium 2+ and calcium. So go down, here's calcium 2+ and calcium, okay, and it is negative 2.868, so negative 2.87 is the value that I'll use there. Okay. So coming over here, we've got negative 2.87. So again, I need to keep in mind what is the cathode and what is the anode in this case. So when I'm looking at it, I can say gold solid goes to gold 3+ ion. So that is a loss of 3 electrons. Okay, that would mean that gold is the anode and calcium is the cathode because gold is being oxidized. Oxidized is anode, reduced is the cathode. Okay, so the calcium value needs to come first in the E cell. Right? E cell is going to equal negative 2.87 minus a positive, so I'll still subtract that in this case, 1.50, right? And so what I end up with is negative 2.87 minus 1.50 is going to give me a negative 4.37 volts. So we finally have an E cell here that has a negative value associated with it. That means I should probably see a positive delta G when I finish this setup here. All right, so let's go back and remind ourselves, how do we set these equal? Delta G equals negative NF E cell. All right, so delta G, which is what we want to solve for here, standardized delta G, is going to equal negative N. Now, let's think about this for a second. What is N? It is the stoichiometric moles of electrons. Well, here, calcium is going to gain 2 electrons, whereas gold is losing 3 electrons, right? Now, gold is losing 3 electrons 2 times, so that's 6 electrons, and calcium is gaining 2 electrons 3 times, so that's 6 electrons. So the stoichiometric ratio of electrons, if I were to write all this out, would be 6. So that's the value that needs to go there. Okay, Faraday's constant is Faraday's constant, so that's about 96,500. Okay, the unit on that is joules per volt mole. And then the last thing I need is my E cell, right? Because this is negative NF E cell. And I said that the E cell up there is negative 4.37 volts. Now, if you take a look at this, right, what I have here, okay, the negative times the negative is going to be positive. So I will indeed have a positive delta G, and that makes sense. If the voltage is negative for the battery cell here, right, that means it's going to take more voltage than it's actually producing in order to drive this reaction. So I would not expect this to be a spontaneous reaction. I'm going to have to input energy from an external source in order to drive this redox reaction here. Okay, so if you put all of that together, you end up with your delta G value, and delta G turns out, when you multiply all this, to be 2.53 times 10 to the 6. Now that's joules per mole. Typically, delta G is reported in kilojoules, so what we will do here is say, or 2.53 times 10 to the 3rd kilojoules per mole, and there is your answer. All right, so hopefully everybody found this helpful in terms of the explanation. Again, the goal here being that we can tie in thermodynamics and the equilibrium constant to the E cell in the electrochemistry, and we can put them all together. All right, so that's about it for this lecture. If you found this helpful, please remember to comment. You can leave comments, like the video. It really helps with boosting the algorithm, and that allows me to make more content. And you can always go and check out our website over at chemcomplete.com. We have got all sorts of free content to help you, and there are also paid guides over there that help support the channel, so I can keep bringing you this content for free on YouTube. So other than that, thank you very much. Remember to subscribe, and I will see everybody for the next lesson. Bye, guys.